Video 5 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the electron charge and current density. The Born interpretation of the wave function tells us that the square of the absolute value of the wave function is the probability density of finding an electron at the point R. Now, if you generalize that to the n electron case, so we have an n, or in general many electron wave function, if we again take the square of the absolute value of our n electron wave function and multiply it with the volume element for each electron, written out here, then this quantity is the probability to finding electron 1 in the volume element dr1 at point r1, and at the same time electron 2 in the volume element dr2 at point r2, and so forth for all the electrons. So this is the probability of finding all the electrons, each of them at one particular point in space. But normally we are not interested in this. We are much more interested in knowing what is the probability of finding electron 1 in the volume end dr1 at the point r1, independent of where all the other electrons are. And if we don't care where all the other electrons are, then we just integrate them out. So we integrate this probability, which we have here, over all the positions of the other electrons, meaning electron 2 to electron n. And then we get this probability here, where P is the probability density, which tells us what is the probability of finding electron 1 at position R1 in the volume element dr1. Now, we cannot distinguish between electrons, and therefore our wave function is made in such a way, or has to be made in such a way, that we cannot distinguish between them. Therefore, if we would now find the probability for finding electron 2 at the same point, this would be exactly the same. And this means if we want to know what is the probability of finding an electron, never mind what we call it, an electron at a point R in a volume element dr, then we just take the probability for one particular electron which we had before and multiply it with the number of electrons. And this P is then the electron density. So the electron density is this integral, an integral over n minus 1 electrons, multiplied with the number of the electrons. This is the exact expression for the electron density, but it's not a very handy expression for applying it to all kinds of wave functions. So therefore let's try to find another expression, and in order to do that, let's remember what the properties of the Dirac delta function are, where here I have generalized it to 3 dimensions. So in general, the properties of a Dirac delta function is that if we have some particular function, f of r here, r a position vector because it's in 3 dimensions, multiplied with this Dirac delta function where we have here r, that's the variable, and then minus r0, which is one particular value of this variable, and we integrate over the whole space. Then what the Dirac delta function does, it picks out the value of our function here for this particular value of the variable, which in our case is sort of a vector. I can use now this property of the Dirac delta function and extend my integrations here to include also the integration over electron 1 here, over the first electron. If I just multiply my wave function here, or the square of the absolute value of the wave function, with this Dirac delta function, where my variable in the Dirac delta function is now the position vector of electron 1, and the particular value, that's my r here. Because the integration over r1 over electron 1 is not going to do anything else than just pick out the value of my function here, which is here the square of the absolute value of the wave function, for the variable that was r1 to have r. So I just get this one back here. Now we can use again that we cannot distinguish between the electrons, and the wave function doesn't do either. So instead of multiplying this integral by n in order to get it for each electrons, I can replace this R1 here by Ri, remove that, and then just sum over I from 1 to n. So I sum over all electrons. That's what I've done here. So here I have my sum over all the electrons, and now I have Ri instead of the R1. And if you look at this now, this is just an expectation value of an operator, which is here our Dirac delta function with for each electron 1. And since this is the density for finding an electron, then this operator, which I have written out here more clearly, must be a density operator. And then I can use this density operator to whatever wave function I'm interested in and calculate the density defined by this wave function just as an expectation value of this density operator. Sometimes, and we will see some applications later on, we need to generalize this definition of the density to something what is called the reduced one electron density matrix. And we have to do that because we need to distinguish between the variable here in the wave function and the variable in the complex conjugate of the wave function. So we have now a quantity which depends not only on the position, one position vector, but it depends on two position vectors, therefore it's called a matrix. Although this is quite a generalized definition of a matrix because the two indices here, if you would call these the indices, are continuous variables. Another quantity which we will use later on is the charge density coming from an n-electron system. And this is of course nothing else than the electron density, which is here, calculated as this expectation value of our newly defined density operator, multiplied with the charge of the electrons, which is minus the elementary charge. The second quantity which we want to introduce here is the current density. And in order to derive an expression for the current density J, here J of R, that is the density of the electric current at each point in space. And you can see this is of course a field because it depends on where in space I am. But in contrast to the charge density or the density, which is a scalar, the current density is a vector, which makes sense because it has a value and it has a direction, and that is the direction in which the charge is flowing. Now, in order to derive an expression for this charge density, we start from the continuity equation of classical electromagnetism, which relates the time derivative of the charge density to the divergence of this current density. And in the following, we're going to derive now an expression for the current density of the electrons. In order to do that, we have to take the time derivative of the charge density coming from the electrons. And as the charge density is given as this integral over our wave function, but now we have to take the time derivative, then of course we have to take a time-dependent wave function. And now we'll go back to the original definition of our probability density and therefore charge density as this integral over the other electrons, 2 to n multiplied by n. So we're not going to use the expectation value expression, but the original expression. And in order to get the something for the current density, now we have to take the time derivative, as I do here. Now, this is an integral over space coordinates. That's a time derivative, so I can interchange the two, which means that, so I can put the time derivative in here, which means I have to take the time derivative of the square of the absolute value of the wave function, which of course is a product, so I have to use the product rule, and then I have to take in each of the two terms which come from the product rule, I have to take a time derivative of a time-dependent wave function. Now you might ask yourself, how do I do that? Well, that's actually quite easy, because that's exactly what the time-dependent Schrödinger equation tells us. Because the time-dependent Schrödinger equation, you can of course read it from h, the Hamiltonian acting on the wave function, but it's much more useful to look at the time-dependent Schrödinger equation tells us what the time derivative of the wave function is. So we can use it here in these two terms of the coming from the product rule, because this is the product here. So we'll get two terms, and the only terms which survive in taking this time derivative are the terms which include the kinetic energy operator of the electrons. Here, where we take the where it's acting on the complex conjugate of the wave function, and here where it's acting on the not complex conjugate of the wave function. All the other terms, all the potential energy terms, they disappear, and that's quite easy to understand. I mean, you're going to derive that in one of the exercises, but it's quite easy to understand because all the other terms in the Hamiltonian, the ones which are not the kinetic energy, are just product operators, and therefore in which order the wave function comes doesn't matter, and they all cancel each other. So we end up with the difference of these two terms with the kinetic energy operator. Now let's remember that the kinetic energy operator, you have a summation here over electron 1 to n, and we want to split up this summation in the term for I equals to 1 and all the remainders, which starting from electron 2 to n, they all vanish here. So the two terms cancel each other, which is the reason for that is that we integrate over that. But you're going to look at that in one of the examples. Back to the continuity equation. Here in the beginning we can see that this is precisely what we need, because the current density shows up here in this scalar product of the gradient operator. And then is the Laplacian, which is the second derivative again. So we have to use the product rule again, and we get again two terms. Then terms. And we can show that all the term sizes. So the only term we are left with is now the one with the Laplacian for electron 1, or the Nabla operators, the gradient operators here for electron 1, and the integrals over the electrons 2 to n. And now we will do what we have done before for the probability density of an n-electron system. We want to extend the integration from being over electrons 2 to n again to the full integration, meaning include also the integral over electron 1. And we do again the same trick as before with the Dirac delta function. So we introduce the Dirac delta function. We actually extend it to summing over all the electrons, because here we have multiplied with the number of electrons, which goes away then. And then I write this Nabla operator again with here the constant in front of it as just the momentum operator. So I get now two terms where I have an expectation value of this operator, which is here the operator with the Dirac delta function, but in contrast to the probability density or charge density, now we have the Dirac delta function multiplied with the momentum operator. And the whole term for the time derivative of the charge density of the electrons is now the gradient operator and the dot product with these terms. So it's the divergent of these terms. And if we go looking at this expression, we can see that whatever we have here in the parentheses, so everything we have in the parentheses, that must be our current density. And here that's the current density where we have a time-dependent wave function, and then for a stationary state we can reduce this by going just from a time-dependent wave function to a time-independent wave function, and here we have the current density for a stationary state.